Good afternoon, guys. Welcome to the IoT Realized Connected Car. This is probably going to be one of the most exciting demos, if it works, of all of Spring 1. It's the only one that involves the potential for property damage, bodily harm, or even death. Hopefully no death, but we do have a real demo with a real car coming up. So let me just take a second and explain who are these people talking to you. My name is Beauregard. I'm a field engineer with Pivotal. What the heck's a field engineer? It means I work in the field. I work with Pivotal's potential and existing customers to help them understand how they can solve their problems with our Pivotal products as well as Spring. So let me also let Michael introduce himself.
My name is Michael Minella. I'm the project lead for Spring Batch. I also contribute to Spring XD and do a whole bunch of other batch-related stuff.
And then we're going to have two more surprise guests joining us over FaceTime and in the room in a little bit. Like I said, it's going to be a live demo, so they'll be joining us in just a couple minutes, and we'll let them introduce themselves when they get here. We also do want to, for the record, thank a lot of other people who made this possible. I know I saw Jamie in here. He helped us with a bunch of the VMs, but this has been a big project with a lot of different people, so thanks to everyone who helped us, from Pivotal Labs to our data scientists and more. So we do have one rule for this talk. The one rule is please ask questions. If you have questions, raise your hands, and we'll do our best to answer them as we go. And then we'll try and save some time at the end for more questions. So let's go back a little bit in time, just so I can tell you a little bit more about how this project started and how it came to be. So this project started actually with us working with a customer. It was a really cool IoT project. You know, when you think IoT, this was the definition of IoT. When our CEO, Paul Moritz, is out there talking about IoT, this is what he means by the Internet of Things. So this is what Pivotal's trying to do. So we were looking at how can we ingest all of this data with many clients at a high rate. We need to ingest it, we need to process it, do math on it, and we want it to feed a dashboard. So we actually worked with a client, we did this, it's really cool, and I want to share it with everyone. Unfortunately, that project is covered by a really ironclad NDA. So after the project, we got together and we said, you know what, we spent a lot on this project, we learned a lot of things, we have some really cool demos, what can we do? So we still want to deal with a lot of connected devices, so a lot of highly concurrent devices. We want to have a lot of clients, and we still want to provide the analytics and feeding the real-time dashboard. So what we came up with is the connected car. So probably pretty much everyone in this room has a car. I'm sure everyone knows what a car is. But more realistically, everyone can think of ideas of what a car does, what kind of information you might be able to get off a car, and what kind of things you might be able to do with this information. So something that's very relatable. It's more relatable. We all know planes and trains and oil rigs, but this is something that's a little more personal, a little more something that we can all think about and work through. So the pieces that we're going to be using in this demo and the project that we've been working on for the past couple of months are the same as the other project. Like I said, I can't mention the other customer, I can't mention the industry, I can't mention what we did, but the pieces and the ideas are the same. So we're going to be using things like Spring XD for doing the ingestion. We're going to be using some sort of storage medium for storing the data, so either files or Hadoop for actually storing all this data we're ingesting. We're going to be using GEMFIRE for an in-memory data grid for actually serving up data to the dashboard. And then we're going to be using HTML, CSS, and JavaScript for feeding a real-time dashboard. So the overall pieces, the overall architecture, the Internet of Things remains the same. Now, I keep saying this Internet of Things. So what is IoT? What is Internet Things? So it's not just refrigerators. Everyone's heard the pitch. My refrigerator is going to be super smart. It's going to have an internet connection, and it's going to send me a message whenever I'm low on milk. Well, I guess that could be convenient, but that's not really going to save me too much money. It's not going to make a difference. It's not going to cure world hunger. It's also not about your toilet tweeting every time you flush. Although there are some companies out of Japan that are making some pretty fancy toilets that can do analysis and text your doctor. Let's not go there. That's not what we're talking about. What we're talking about is operational efficiencies. So how can we make big and little differences using always connected devices and bring these to other industries for operational efficiencies? So one of our parent companies, GE, has put together a nice video kind of shooting for the moon about what's possible with the Internet of Things. You may have seen this already, but we'll go ahead and play it for you.
My mom, she makes underwater fans that are powered by the moon. My mom makes airplane engines that can talk.
Ladies doing the job. Thank you.
My mom makes hospitals you can hold in your hand. My mom can print amazing things right from her computer. My mom makes trains that are friends with trees. My mom works at GE.
Have you guys seen that commercial? Excuse me. So yeah, it's a GE ad. It's, you know, a bit out there, but it's kind of conceptually some of the things that they're working on. And as I mentioned, GE actually is one of the owners of Pivotal, so they are actually using the technology that we're talking about today and that we are using for this project under the hood of all their projects for the Internet of Things. And one of the things that they frequently talk about and we'll talk about is what could we do with 1%? So 1% seems like a pretty trivial amount, but if you look at some of the Internet of Things use cases, we're talking about huge scales. So what could we do if we could save 1% on airlines? Or what could we do if we could save 1% on oil or gas? So 1% actually becomes a big deal. So it's not that you're automatically going to get 1% for free, but looking at what changes can we make, what learnings can we make that could make a 1% or 2% or a 3% improvement over the status quo, over what we're doing today. So bringing that back to the connected car, let's look a little bit about cars. So in 2010, the last time we did the US census, there were 1 billion cars on the world. We just crossed that 1 billion mark. So by far, most of the cars are in the United States. So there's about 240 million cars in the US. But China is by far the fastest growing area. So about 50% in growth in the number of cars is coming from China. And they're growing at about 28% per year. So with the way it is now, US is still #1 per capita. But if China catches up, and it's a real possibility that they will catch up per capita, that would be an additional 1 billion cars on the road. So if you add that up, 2 billion cars, that's a lot of cars that we're heading to. So in order to support 2 billion cars, we need 120 million barrels of oil per day. So if you multiply that out at $100 approximately per barrel, that's about, what was that? That is about $12 billion a day that we're going to be spending just on crude oil. So let's think, if we can do some things with cars from sensor data and improve that by just 1%, that's a $120 million impact that we can make per day. So let's think of some ideas of what we can do with cars just to make that impact. And that's only the cost of the oil, not to mention the environmental impacts and saving your time and whatnot. So basically, we want to start with a car, and we want to start to get sensor data off that car. So we need to capture that data. We want to stream that data up into the cloud, up to our servers. We want to store that data for later analysis, and we want to be able to do real-time analytics and feed a dashboard. But right now, that's enough of me talking. We'll tell you how it's done in a minute, but we actually want to show it to you first. So let's bring in our guest speakers here and do a demo of this. So bear with us for 1 second while we flip over. Hey, Phil, Darrel.
Hi, everyone.
Hey guys.
Can you guys hear us okay over there? Excellent, excellent. Welcome, everyone. So what we thought we'd do is tell you a little bit about what we're doing today here in the car. So we are currently in a 2010 Ford Expedition, and it's owned by my partner here. My name is Philip Berman, by the way. I'm a field engineer I work for Pivotal. Darrel, why don't you introduce yourself?
I'm Darrel Sharpe, field engineer. I live in Texas, and I have a car.
All right, we're kind of in Darrel's hometown here. We're in Richardson, Texas. Darrel actually lives in Garland, but they're sort of in the same neighborhood. And what I'd like to do is tell you a little bit about what we're going to do. So the first piece of the puzzle here is this this BT1A dongle from GoPoint Technology. And what we do is we plug this into the OBD2 port. The OBD2 port is in every car since 1996. And if you've ever taken your car to have the emissions tested, or if you have an engine light on and you want to find out why it's on and you bring your car to the shop, they plug into that port and it does reading of sensors off your engine. How are we doing so far? Can you still hear me?
Yep, you're good. Keep going.
Excellent. So we're going to plug this thing in now, and then we'll move into the next piece of the puzzle. So why don't we turn off the car, Derek? Darrel? Sorry about that. We're not that connected. All right, so plug it in. All right, so that thing is plugged in. Go ahead and start the car back up. All right, so the next thing we're going to do, we're going to turn on an iPhone app. So we have an iPhone app developed by Pivotal Labs. Pivotal Labs is our agile development company. They do a lot of great development work. And they built an iPhone app whose job it is to connect via Bluetooth to this E1A and then convert the data to JSON, do a few other enrichments that we'll talk about later, and send the data up to the server, the Spring XD server. So what I'm going to do now is I'm going to show you that right here. So here's the iPhone, and here's the little P for Pivotal, and we nicknamed this app Herbie. So I'm going to start Herbie up right now. Herbie's going to connect, like I said, to Bluetooth, and via Bluetooth to the dongle. And when you guys are ready there, I'm going to start this up. But before you tell me if you're ready, I just want to let you know that the game plan here is we're going to see if the data science and machine learning can actually predict where we're going. So we're either going to be going for beers at the Flying Saucer. We're going to be going potentially to an Indian restaurant for some food. We may alternatively go to Babe's Fried Chicken Dinner Place, or we could be going to the Omni to go to work. We'll see. So when you guys give me the hi-ho, I'm going to start this thing and see if we're streaming the data.
We're good to go, Phil.
All right, turned it on. Tell me you guys see something over there.
We see data.
Let me flip over to the
All right, what do you guys think? We'd like to rev up the engine here to just kind of prove it. Should we rev it up to 1,000 RPMs, 2,000 RPMs, 3,000? What do you guys think?
Really quick show of hands. 1,000? 2,000? Everybody wants 3,000.
All right, let's go to 3,000.
So this is real time. This isn't some recording.
All right. Thank you for that applause. I think that's it now for our FaceTime. For now, I'm gonna see here. I'm gonna turn this around, and so you can see where we're going. And I think, did I leave anything out, or should we start driving?
Go ahead and start driving. We'll show that the dot's moving, and then we'll get into the dashboard a little bit.
All right, here we go. In all our testing, there's usually someone who walks right in front of us at this point, but
Better luck this time, huh?
yeah.
Wait till they turn. The bodily harm piece comes into play right about now.
Yeah, it's going to be really tragic if something bad does happen. You guys.
All right, Phil.
But,
Unless you guys have anything else, we're going to bounce back and I'll start walking through the dashboard.
all right, if you want to periodically flip back and watch where we're going, otherwise we'll let you know when we're about a minute or two out from wherever our destination is. You're going to have to predict.
All right, thanks, Phil.
See ya.
I'm going to leave this up, the FaceTime up, and we may flip back and forth as things go on. But let's really quickly walk through the dashboard as far as what we're actually streaming here, what's going on. To start off, we've got obviously the map itself. That's showing real-time data with regards to location. Along the right, we've got a collection of gauges that are displaying real-time data. The first one being the speed. Second one is RPMs. And then we also have coolant temperature, so the engine's the coolant temp, as well as the fuel level. Ooh, actually, that's kind of interesting that they're so low. They didn't refill. Hopefully, it's a quick journey. So that's the first tab. The second tab is, frankly, the little more interesting one. So this breaks us out to a bigger view of Dallas. And each one of these orange markers is a potential endpoint to where they could be driving to. It's based on historical data. Along the right, we've got the instantaneous miles per gallon. So if you've ever paid attention, if you've got a recent enough car, the gauges, or it'll show you your current driving miles per gallon. That's what we're displaying here. You'll notice that because it's instantaneous, there will be wild fluctuations. If you're coasting on the highway at 60 miles an hour and you take your foot off the gas for just a second, it's going to think you can go 60 miles an hour for a long period of time, so you'll get a great gas mileage. And if you're accelerating, it'll drop really fast. The predicted range is based on where we think you're going. So what we're doing is we're trying to predict where you're going, and then based on the driving patterns, traffic patterns, et cetera, of that drive, we're using that to impact the predicted range. So right now it's at about, it's bouncing back and forth. We're at about 50%-ish the Omni Hotel and 50-ish% the Flying Saucer. And based on instantaneous data, it seems to be bouncing back and forth. Anybody have any questions on the functionality before we get into actually how this thing works? Yeah.
Where is the GPS data coming from? Is it the piece plugged into the car or the phone?
We'll get to that in just a minute. Good question. The question was, where's the GPS data coming from? And we'll actually talk about that.
How did you come up with the endpoints, multiple endpoints? And how did you compute this?
So the endpoints are based on historical data. So we actually recorded a number of journeys. Imagine if, as you drive your car, there are going to be places where you tend to go. Not only tend to go, but you tend to take particular paths. You tend to go to these places at particular times. Like at 8 a.m. on a Monday morning, if your car's in the driveway, there's a good chance you're probably going to be going to work. Exactly, yes. Other questions about the functionality before we get into how it works? Yeah.
Potentially, is this something like where you work with Waze, how they do predictive driving as well, as far as driving patterns and stuff like that?
Yeah.
That you could kind of work them together?
Yeah, not only Waze, but Waze, this is actually kind of how you could implement a Waze if you wanted. Okay, so now you guys are familiar with what we're doing. Now let's talk a little bit about how it works. Let's start in the car. The car is, like Phil said, the car, and every car sold in the US since 1996 has what's called an OBD2 port in it. OBD stands for onboard diagnostics. There's actually, so I'm going to pass around an example of the dongle if you guys want to take a look at it. Thank you. This port exposes a number of analytics: RPM speed, mass airflow sensor, data, all kinds of different analytics, as well as some things like the VIN of the car, as well as the state of certain things. If you go to get your emissions tested, if your state does emissions testing, chances are they're just going to plug in a plug into that jack. All that's going to do is it's going to check the state. Basically, is your check engine light on? Has it been on recently? And are all of the emission components reporting that they're operating correctly? If those things check out, you're probably going to pass your emissions test. Unfortunately, the API for dealing with OBD2 is really low level and cryptic. It's actually a TCP connection that we create. And what we do is you pass what's called PIDs or parameter IDs to the car, and it replies back with the values. So this is an example of an exchange to get a piece of information via OBD2. The top in the yellow is our request to the car. So it's broken up into 2 bytes. The first byte is hex for the mode of the PID that you want. There's 9 modes. 1 is where most of the PIDs are that we care about. That's the real-time current state of things. 9 is another common mode that you'd hit, which has things like the VIN number and static data. One of the other modes actually has the trouble codes that your mechanic would pull when your check engine light's on. So in this example, 01 is the mode, 0D is requesting the speed. So that's the PID ID for the speed that we're asking for. The response back that we're going to get is everything in the blue and the orange. The blue, they start off by echoing back the exact request. The rest of the blue on the second line is metadata about it, the length of the message, and so on. Where it gets interesting is at the 4. So 4 indicates from here on out is the actual data you requested. It then echoes back the mode. So in this case, 1, we requested mode 1. 0D is the PID we requested, so that's echoing that back. And then 30 is the hex value for the speed in kilometers that the car is currently moving. If we convert that to decimal, that's 48. And conveniently, if we convert that from kilometers per hour, which this is in, back to miles per hour, it's actually 30 miles per hour. Does that make sense? Yeah.
Is that spec by OBD2, so it's actually standard across all makes and models?
Yes. So the question was, is this a spec that's universal across makes and models? The yes and no. Yes, there is a standard. Yes, it is OBD2. Yes, cars do implement the standard. However, we've found both researching and plugging this thing into different cars react different ways. Different cars expose different PIDs. There's a whole collection of custom PIDs that manufacturers can add. We found, I mean, for example, on my cars in testing, I was able to get the VIN reliably. We haven't had a Ford yet return a VIN number. So let's take a quick look at like I said, this is a pretty low-level API. I want to show you an example of our version 1 of this. Phil in the car right now, where is Phil at right now? He's on the highway. So Phil is using what is version 2 of this code. Version 1 was coded with me in my driveway with my laptop and that dongle that's getting passed around. So I was freaking out the neighbors as I'm the guy in my car with a laptop. But so what we did was to kind of reverse engineer how this works. I took the dongle and I took an iPhone app and I recorded the traffic, the Wi-Fi traffic between the two, and reverse engineered the kind of kabuki that needs to happen to establish a connection, and then understand the loop of it asking for these PIDs. All of this is a Spring Boot application using Spring integration as the communication piece, so it's actually really simple from a communication piece. The hard part was dealing with the OBD2 issues. I'm not going to go through all this code because, like I said, it's really cryptic and low level, and we're not actually using this today, but I just wanted to give you an example. So we've got the main method, it's a Spring Boot app, and we kick off a while loop that's just continually polling the car. Within the car, we're doing this get state, and this is where we're actually asking for each one of the PIDs. So all we're doing is this gateway is a TCP gateway using Spring integration, and we're sending requests. So get RPM is going to send 010C. We get the response back, and we decode it. That's really all this is. And then you'll see down below, if you were to get this code, there are different decoding things you have to do for each individual PID. Some of them are binary flags. Some of them are, for example, the version of OBD2. that you actually have to take the hex value, convert it into decimal, and that translates into the version of the OBD2 spec you're using. There's OBD1, OBD2, both supported. There's European OBD2, there's Korean, there's a whole laundry list of them. So that was version 1 of the code. Like I said, it's very cryptic. I didn't want to spend a lot of time going through the code itself. I just want you guys to get a feel for the low levelness of it. Right now, Phil's actually using an iPhone app inside the car to interface with the car, as well as then stream the data back to our server. This is actually a screenshot of the application. It's really pretty straightforward. We've got a start-stop button at the top. It's the start-stop of the streaming. Below that is the IP import of the server endpoint that we're sending the data to. Below that's a little slider. Going back to the, is OBD2 a standard? One of the other things that we've found is just the rate of querying we can do with a car varies vastly from car to car to car. So we use a slider basically to throttle how often we ask the car for PIDs. The last piece is just some output. It's purely for debugging. It's displaying the JSON that we're going to send back to the server. To answer the question about the GPS, so GPS is not part of the OBD2 standard. So we are enriching the data on the phone with GPS and acceleration. Those are the two values we're getting from the phone itself. There is an alternative. I probably shouldn't call it an alternative, but there is another open source-ish project that Ford's currently working on called OpenXC, or I forget the exact name of it. But it does a couple things. Number one, it wraps OBD in a much nicer API. It also exposes a lot of this from the car. So if the car has navigation built in, there's no reason not to use its GPS coordinates. So it exposes some of that directly out. But the reason we didn't use that is, number one, it's not universal. It is across, it's not universal across cars. It is something that only Ford is working on. And even within the Ford models, there was a big variance between what was supported and what wasn't supported. And so we wanted to make sure that we got something that we could translate, because like I'm testing with my personal cars, we've tested with a number of cars, and we weren't sure what we were going to actually work out with. Question in the back. Yes. Yep. With the newer cars with the black box thing, I honestly don't know. I don't know how far back they're recording that type of stuff. We'll get to an entertaining example of that towards the end of the talk. Yeah.
You mentioned that the speed and acceleration is covered by the phone, so I thought OBD2 does report speed. It does not.
It reports speed. It does not report acceleration. Acceleration is the change of the rate of change. So yeah, so we're actually using the internal iPhone sensors for that. Just to switch back really quick, they're on the highway. Let's see how our prediction's going. Let's see if we know where they're at. Well, we've kind of decided where we're at. And it is, whoops. Phil, we're looking at the dashboard. You guys are actually getting pretty close to the Omni, it looks like, right? Hey,
I'm going to turn it back around. What's that?
Phil, you guys aren't, but the dashboard is. You are on speaker, though, so it looks like you guys are going to the Omni Hotel. No drinks today?
Yeah, it's a little early for the flying saucer, but maybe later.
All right. So as you can see, we've predicted the Omni Hotel via the analytics, and they're about maybe 10, probably 5 minutes away at that point. All the others are showing 0. And based on that, we predict that with the gas they still have in the tank, they would be able to hit about another 150 seconds. So here's Here's an example of the JSON. I don't expect you to be able to read it. This is more for documentation purposes, so when you get the deck later, you can read it. But this is an example of some of the stuff we're sending back. So VIN, lat, longitude, throttle position, acceleration, vehicle speed, mass airflow sensor rate, fuel usage rates, all those types of things. Those are all in that JSON they were sending through the phone to the car, or to the server. From a communication perspective, the car is communicating to the phone via TCP socket over Bluetooth, and we're doing just basic HTTP posts over cellular network to the server. Nothing fancy on that end. We considered like MQTT and stuff like that. We just didn't need it. Yeah?
What's the frequency of that HTTP post that you guys are doing?
Right now it's once a second. Yeah. So let's talk about what's on the server. As Derek mentioned, that we're using Spring XD as the ingestion tool on the server. The reason for that is it does this type of stuff and makes it really easy. When you think about a big data application, you could have data in databases somewhere. You could have sensor data like we're streaming. You could have other data that we want to aggregate with, like traffic data or other users or whatnot. We want to call APIs. We need to get all that data together into somewhere where we can do big data processing. Once we're done with our processing, we need to export it somewhere where we can drive a dashboard on top of that. That's kind of this end-to-end solution, right? Spring XD is designed from the bottom up to basically handle everything underneath the white circle. So ingestion, orchestration, extraction, all with real-time analytics. Spring XD is a distributed runtime, so it's not a bunch of jar files you include in your applications. It's actually servers that you install on your machines. We'll get into some of describing a realistic topology of this towards the end of the talk. It supports streaming and batch modes. If you went to my recommendation talk earlier today, you saw a bunch of the batch stuff. This is obviously streaming real time. There's a number of ways to interact with Spring XD. We've got an interactive shell, as well as a web UI. Both of those sit on top of a collection of RESTful web services that you can consume directly as well. The stream definitions that we're using are surprisingly simple. We've got the HTTP source that we're using. We're using it out of the box, so we haven't configured anything additional. So what that's going to do is it's going to open up a port, specifically port 9000, and listen to any data that's posted to that endpoint. Anything that gets, it's going to pass on to our transformer. I'll show you the code for that in just a second, but the transformer, all it's doing is it's adding a GUID and a timestamp. That's it. We then pass that on to object to JSON. We are using a domain object in here, so we need to convert it back to JSON. And then we're sending that out to Rabbit. Once the endpoint that's using Rabbit is done with it, we've got another Rabbit queue that's replying back. I'll get to what the Rabbit piece is doing in just a second. The Rabbit piece then reads that off and writes it out to a file. Right now we're just using straight files. In a future version of this, we'll be using Pivotal HD with Hawk and much cooler stuff. That second stream definition, we're also tapping. The tap for this is going to create a copy of everything that goes to the file and send that to GEMFIRE. We're doing that to power the dashboard. The GEMFIRE is actually where the dashboard is querying for the information. The dashboard is the data source for a REST API that the dashboard consumes. So continuing to look at the server as far as these pieces and containers and stuff, right now we're running all single node on a single VM, really just because we only have one car running, there's no need to. We'll get into, like I said, more realistic deployments in a bit. But we've got Spring XD, we've got HTTP sending to the transformers to Rabbit. Rabbit then sends it out to a Python process. The Python process is what's doing the predictions of the journey and that type of thing. So we send the data out to Python. It does its magic and replies back via Rabbit, which then sends it on to the file, which we write out to the file system. The tap for GEMFIRE then writes that out to GEMFIRE, which via a REST API powers our dashboard. Does that all make sense? The cool thing about this is the boxes in green are the only places where we had to write custom code. All the rest of this comes out of the box. We didn't even really have to configure much, to be perfectly honest. The transformers, like I said, I'll show you that in just a second. The Python code and the dashboard, to be perfectly honest, I think the dashboard has the most code out of any of it. If you pull up our GitHub repo and see the language breakdown, I think JavaScript is the largest language in our project.
Do you want to check back in on Phil?
See if he's actually here? Sure.
I believe they are close.
Let's see where we're at. Yeah, they are very close. Hey, Phil. Can you hear us?
Yeah, we actually took a wrong turn. But now we're coming up on a railroad crossing here. It looks like the railroad just went by. So I'm glad you find that humorous.
The perks of live demos.
What would you like? Just wondering where we are?
Yeah, so I'm assuming with course correction, you'll be here in a couple minutes then?
Yeah.
Okay.
We're about, it says we're 2 midway.
Okay, so then we'll see you when you get here.
Okay, sounds good.
All right. Pardon? The dashboard is not rendered on the mobile. It's a separate application. Within the car, so the question was what is the iOS app get? It gets nothing in return. It's simply a middleman just chucking data over the wall. It doesn't care what happens afterwards. So, yeah. It could. It's just that they could also be consuming the dashboard itself. In an earlier version, if you go to the demo lounge and check out, we actually have this whole thing set up on there. You can actually check it out, and we can dig even deeper there. It's got an older version of the code, and that dashboard is actually iPad friendly. They could have it, locally. There's nothing stopping us from, with a few tweaks, this would be responsive, and it wouldn't be. They'd have all this information with them. So let's take a quick look at the transformer we're using. Like I said, it is painfully simple. So all this is a Spring integration transformer. It takes a message, we crack it open, we convert it to, it's JSON as the payload, so we parse the JSON into a map. We add in a timestamp, a GUID, wrap it back up and send it on its way. That's it. That's all the processing we're doing on the server right now. Obviously, there's a lot more we could do, but that's all we're doing right now. The other piece to this is the data science piece. The data science piece is adding two pieces of functionality. The first one is predicting the journey, so where am I going to end up? The second one is based on that journey, what is the range of what I currently have? So how far can I go on my tank knowing where I'm going? How does that work? It starts off by storing the sensor data. So the dashboard is powered completely off by GEMFIRE. So why are we storing the stuff in a file somewhere, right? The reason we're doing that is because the data science model gets trained periodically with that file-based data. So basically, once a night, we would run an offline training process that generates the metadata that we use to evaluate the real-time stream to determine where they're going. When the journey starts, we start off with an initial prediction. So like I was saying earlier on, it's 8 a.m. in the morning, you're in your driveway at home, you're probably going to work. It's 5 o'clock on a Friday, 50-50 shot, you're going to the bar or you're going home. So we start off with an initial prediction to get things started. As you drive, we refine that prediction and basically create a secondary prediction that the weight shifts over time from the initial prediction to the real-time one, essentially fading out that initial prediction. Does that make sense? This is, so I showed you a quick shot of the JSON before that we sent from the phone. This is what we add with the Python piece to the JSON. So this is a list of predictions. Each prediction essentially has an endpoint location. So that's the GPS endpoint of the endpoint that we could end up at. It's got miles per gallon for the journey, which we'll then use with the math of how much gas you've got left. That's what we'll use to calculate the range. And then the probability of the prediction. So how likely is this going to be your endpoint? The real-time dashboard, we already talked a little bit about that. It's powered by GEMFIRE. We use GEMFIRE specifically because the vision of this is to have lots of clients and lots of data coming in very fast. The NDA client, that was the scenario, and we've talked about use cases where that would be the case as well here. For example, if you wanted to have an app like this where your clients were all the taxis in New York City. That's going to be a lot of data, very frequent updates. GEMFIRE handles that type of data scenario use case really well.
Michael Phil's walking in if you want to check on the video.
Sure, why not?
See if they have connectivity.
They're coming up the stairs. I'll have that up small while I continue to talk. The other pieces of the dashboard are REST. Yeah. So the question was, how many updates are we getting from the car per second? We're getting 1 update per second. But like I said, if you imagine like all the cabs in New York or whatever, that obviously could get very fast. The client that we can't talk about, we'll get to the scale in a bit. There's a whole section about that. So GEMFIRE is the data storage piece. We're using a REST API to expose this data, both. Like I said, we've got a REST endpoint that provides both the list of the possible journeys as well as this data we're getting from the car. We used Yaumin to generate the site with an Angular JS JavaScript library. For the record, the version that's in the demo lounge uses a jQuery earlier version of the dashboard. We should all turn around and watch him come in, because he has no idea. Good, we're waiting on you. All right, come on. You wanna? Next part's yours, or do we wait? Or we can wait. While we're waiting for their grand entrance, any other questions before we move on?
So you said you're putting HD nodes once per second.
Yep.
But you're fetching data from the car faster than that, right?
We actually aren't.
Or you're not? No.
Well, part of what we have to do with the car is you fetch the PIDs individually. So it's many requests to the car to get the full message that we need to send over the.
Nope. So the question was, on the Herbie app, that slider was showing about 100 milliseconds. The question is, are we querying the car? So the question was, we're querying the car faster than we're sending data, so why is that? The reason is because we're not getting the full request in a single shot, so we actually have to ask for PIDs. And the OBD2 standard allows you to bundle them, but even with that, again, depending on which car, the response, we were getting actual errors, so we cut it down so it is asking 1 PID at a time, and because of that, we need to basically, as soon as we get everything, we check it the next one. Any other questions? Yeah.
How is it determining the endpoints? Like you said,
So the way we're doing it is actual journeys. So basically, she shut off the car.
If you want, I can add a little color on that. I know Roner in Germany, data scientist, who figured this out. What he originally did was he, for about 5 months, he recorded his journeys back and forth in Berlin to work. And then he ran tests and realized there were clusters of journeys around typical journeys that he takes. For him, he was driving to work every day and then going to watch the World Cup and drinking beer and then driving home in the evenings. And then on the weekends, he was driving in the country. And it was actually a German car manufacturer was working with the data scientist to come up with a more accurate range prediction with a lot of the electric cars. It's really important that you don't run out of battery juice. So that's how we came up with it. It was through the most common journeys.
Other questions before we move on? Cool.
All right. So legal disclaimer there, no engineers were hurt in the making of this, and none today. And Phil had a designated driver, so it would have been okay if he drank. All right, so let's talk a little bit more about what this would take to make it real. So right now we're just looking at one car, one message a second. Seems like a lot of overkill, everything we've done here. But if we look at what it would take to scale a solution like this or to scale an Internet of Things solution, we're talking, when we're talking about cars, I said we're growing towards 2 billion cars. Now we're not going to be tracking them all. We're not the NSA. But we're talking hundreds of thousands of clients, whether it's cars, plane engines, oil rigs, whatever the thing is in the Internet of Things. We're talking hundreds of thousands that we're going to be getting data from. And it's not just one message a second. Right now we're looking at the car for one message a second, but clients we've been talking to have multiple seconds, 5, 10 messages coming per second. So it's hundreds of thousands of devices times multiple messages per second. So we're looking at millions of messages per second. Now each message is fairly small. In this case, we're talking about probably single-digit kilobytes for the actual JSON message. You can compress that, you can turn it into a better format like Avro or Parquet or some sort of serialized zip format. But when you multiply that by hundreds of thousands of devices, many messages per second, you end up with hundreds of gigabytes of data per minute. So we have to be able to ingest, process, run math on, and store all of this data. So this is why we start to talk about things like Hadoop, because we are going to be storing gigabytes, terabytes, and petabytes of data. And we want to store it all because we want to have a really nice model. And one of the sayings about models is it's better to have more data to improve than to improve your algorithm. So we want to store it all so that we can continue to run our model on it to get better predictions. So what does this actually start to look like in a more realistic deployment using the technology that we've talked about? So we basically have the stream that we define, the HTTP to the transformers, to Rabbit, to file with the taps. That gets decomposed into the modules. And each of those modules are communicating via RabbitMQ. So when you go in through the admin console, you deploy this stream. We're ending up with default with one instance of each module, and each module talking to RabbitMQ. So how do we actually start to make this faster? Or how do we make this scale? So some of the things we've looked at is you can make the payload smaller. So just like many other things, the smaller the actual message, the faster things go. And also the amount of processing that you're doing on the messages. So a lot of times we've seen that the messages come in some format, some serialized format. We then have to deserialize them to do our processing. And then maybe we're re-serializing them to Parquet or something to put them back into HDFS. So you can end up with a lot of different I/O. And there's different trade-offs here. So in the default drawing that I showed before, we're doing lots of network hops. And you may have RabbitMQ set up to be fully redundant with disk storage so that you've got reliable transmission, but you're trading performance for some of the data guarantees. As I mentioned, by default, it's going to be putting everything on Rabbit, and that ends up being a lot of network hops. So basically, every message between every module in the stream, we're bouncing off of RabbitMQ. So 2 network hops plus hitting RabbitMQ. If RabbitMQ is making redundant copies or storing it to disk, that's adding in additional overhead, additional latency, and affecting how much we can process. So a nice thing about Spring XD is you can start to compose these modules together. So we can say, well, you know, for the HTTP transformers and rabbits, we want to compose these and co-locate these all on one node. So that means as a message flows through them, you're not having the extra overhead of network hops and going to Rabbit, but we're still going to bounce that out to RabbitMQ at certain places. You can almost think of it as checkpointing it to be able to pass it through RabbitMQ, but it also gives you other benefits. Here we're going to send it off to Python again for our data analytics, and then as we start to send it off to the file and GEMFIRE tap, we'll use RabbitMQ for that. So again, it really comes down to trade-offs. So do you want really high availability? Do you want guaranteed message delivery? Or are you looking for the fastest performance that you could get out of the system? So there's, again, going to be a lot of knobs and dials we can do to start to tune this thing. Also, we're going to talk about high availability when it comes to scalability. Like I mentioned, it's a bit of a trade-off on some of the issues there. But how do we start to make this more highly available, and how do we actually start to scale it? And part of this is that we start to run multiple instances of our modules. So using Spring XD, we can run multiple instances of our stream in each of the modules. And in this case, we're showing 3 instances of the main HTTP and Rabbit, and then perhaps 2 instances of GEMFIRE. Mark Fisher's keynote last night had a great demo of scaling these things for scale and availability. But I also want to point out some of the other things on here. Zookeeper and running the Zookeeper cluster here. So we do also have the cluster and the reliability that provides. RabbitMQ, I'm not going to get into the details. That would be a whole nother talk. But using RabbitMQ and clustering with RabbitMQ to also be able to scale that solution and also get into higher availability. And then also with GEMFIRE, running it in a GEMFIRE cluster. So that may seem overkill just for driving a dashboard that's showing one car. But again, when we get into hundreds of thousands of cars, millions of messages, running a cluster that can, again, scale horizontally and have the availability becomes very important. So questions on some of the things we were looking at with scalability and availability? All right, so what were some of the issues and challenges that we ran into and that we foresee with other Internet of Things solutions? The first one is connectivity. So a lot of the things that we're trying to get information from don't have connectivity. So for example, our dongle doesn't have built-in cellular connectivity or Wi-Fi connectivity. It has Bluetooth. So we really had to bridge that connectivity gap from the Bluetooth to the cellular network using the cell phone. But if you look at other things, whether it's plane engines that might have to communicate via satellites or not at all, or it's oil rigs or trains that may be up in the northern part of the US that doesn't have good connectivity with internet or Wi-Fi, there's going to be a gap in connectivity. And a lot of that connectivity, if it's satellite or remote connectivity, is going to be intermittent, kind of flaky connectivity. So those devices may have to have some sort of bridge, or they may have to kind of batch up the messages while they're offline and then send them in micro batches or batches back to the server. So our server also needs to be able to account for that. So if something goes offline because it's lost connectivity and it's batching them up and then sending them in batches, we need to be able to handle those batches rather than the individual messages. Compatibility, as Michael mentioned, was a big issue here, and we could foresee that with other devices. So ODB2 is a standard. It's supposed to be in every car since 1996, but cars have implemented that standard a little bit differently. Different cars have implemented different subsets, or they've extended the standard. Actually, some cars we've seen, they've added a lot of really cool extensions to it, but then they charge you for the documentation. So if you actually want to know what the other PIDs are, what the other values are, and how you could use them, you got to pay them a yearly fee, and that can be really expensive for the little guy. Some of the cars don't give you the VIN number. We get a VIN not yet supported, and other fields are hit and miss between cars. So it really varies from car to car, from year to year, and a lot from manufacturer to manufacturer. So we had to test with the different cars. We had to make sure we had Darrel's standard car for this demo so we knew it would work with the fields that we were trying out. And also the dongle, I think we passed around one dongle. We had a different dongle here. Each dongle behaves a little bit differently, and each application that the dongle provides with it behaves a little bit differently. So a lot of compatibility issues and a lot of testing issues. You know, a large amount of our work went into that actual bridge between the dongle and getting the data up to Spring XD. So looking towards the future, where are we going with this project? And this isn't something that ends today. This is something that we're going to continue to develop. The next big thing is we're going to start dropping this data into Hadoop. So it's going to grow from just one card to many cards and lots of data. So we want to drop all of this data down into HDFS. And then we're going to move our batch offline training to actually operate against that data living inside of HDFS. The other nice thing about Spring XD being a kind of big data solution is we can actually move the scheduling and the operation of that batch training into Spring XD. So we can say every night or maybe every hour, we want you to rebuild the model, pointing it at the data in HDFS and updating kind of the operationalized version that we're using for our calculations in the stream. So it can really go full circle with that process. So we've also thought about some additional use cases that we might do with the connected car in this type of solution. The first one's around driving efficiency. So we're getting a lot of information here corresponding to acceleration, the speed, the location, gas consumption, all this information that we can start to bring together to help encourage and give instant feedback on driving efficiency. So we can look at the gas mileage you're getting, we can look at how fast you're accelerating and make the quick correlation, hey, don't accelerate so much and you're going to get better gas mileage. So we can start to use a lot of this data to give instantaneous feedback, as well as start to build additional models based on your whole history of driving to tell you how efficiently you're driving, what things you could do, what things you could change. Another one that we mentioned earlier and got some feedback on was traffic patterns. So this could be twofold. One, this could be looking at where you are, what the predicted route we think you're taking is, and then tying in what we also know, whether it's from Google or Waze or what we're collecting about the existing traffic, and can help look at different traffic patterns, give you better predictions, better range predictions, or even better routes based on what we know about where you are and where we think you're going. But because we're also collecting all this data, we can also feed that back in to help create some of that information. And that kind of goes back to Waze, you know, pooling all the information from all the different cars we're monitoring to kind of build up these traffic patterns and look at the current traffic. Another fun example is gas pricing, and this one actually comes from Phil. So Phil lives in Chicago. So most of the week he's driving around Chicago, going to talk to customers. He's in the city, he's getting really bad gas mileage. Gas is really expensive in Chicago, right? But he lives right next to Michigan, and because all the car companies are there, they have great gas, really cheap gas in Michigan. So on the weekends when he's going out to his place in Michigan, if he gets across the border into Michigan when he refills, he can save a lot of money on gas. But the big question is always, will he make it to Michigan? And I don't think you want to get stuck halfway in between Chicago and Michigan, right? You're in Gary, Illinois or something. But so he looks at his car, he looks at the range that his car is telling him. And that range is not showing very far because he's been driving in the city all week getting really bad gas mileage. So it's saying he's not going to make it. But he's learned that once he gets on the highway, once he gets going, that gas mileage is going to explode because he's getting a lot more efficient driving. So he'll actually be able to make it. And this was a bit of the catalyst for some of the work we were doing, is if the car can say, oh, it's Saturday, Phil's driving to Michigan, let me make a more intelligent guess about what his gas mileage is going to be based on more information and more logic than just, you know, his past couple days of driving. So can affect when Phil gets gas at least. And another example here we're going to play a video for is if we detect an accident. So if we had seen a very sudden explosion of acceleration in their driving or a sudden change in direction, we might have known something's wrong.
This is a video that was played. I believe it was either VMworld or EMC World the past year. It's a fake thing. This doesn't really exist, but you can get the idea of where people are thinking about it.
okay?
Yeah, you? I'm good. Oh, no, not you. Listen, I'm gonna have to call my agent. I'm gonna get right back to you.
Mr. Burton, this is Insure Corp. We've received sensor data that indicates you were in an accident. Are you injured in any way?
I'm not injured, no.
Is anyone else injured?
I don't believe so.
Okay, where's my agent's number?
We have pinpointed your location, and we are showing your car is not drivable. So we are dispatching an Uber car to take you to your destination.
That would be great.
I'm pressing 1. English. E-N-G-L-I, English.
May we give your coordinates to our appraiser drone to perform the appraisal?
Absolutely.
We have received the photos, assessed the damage, authorized the repair, selected a qualified repair facility, and have dispatched a tow truck to take your vehicle to that facility.
Perfect.
Yes, hi, this is... Yes, I'll hold.
We have looked up the other vehicle's insurance, transmitted the appropriate data to create the claim, and filed the California SR1 accident report. Can you confirm the information is correct on your phone, then hit the accept button?
I'll check it right now. Okay, all done.
Thank you. Your Uber car is arriving now.
I see it coming.
Accident, not payment, accident.
Your tow truck should be there now. Don't forget to leave your keys in the vehicle. Thank you for using Insure Corp, powered by Pivotal Labs.
Wouldn't that be nice? In a way, it seems like we're really far from that, but all the pieces are there. Now it's... You want to throw the slides back up? You know, we're getting that information. We can hook into Uber. We can borrow an Amazon drone to go take pictures. You know, it might not actually be that far. And it could save us money, but definitely a lot of a headache. So IoT is everywhere. You know, we talked a little bit about saving money with gas. This one was looking at insurance, but it affects every industry, and it's all across the globe. There are different applications pretty much anywhere you look. This is an infographic, maybe a little bit hard to read, but this was put together by General Electric and World Bank, and it was breaking up the global GDP, and it started to look between developing economies and advanced economies, and then break them up by industry and start to look at where different areas that might be applicable for the industrial internet or the Internet of Things might apply. So they were singling out their particular industries, but healthcare, transportation, manufacturing, and then general other, but looking at the dollar amounts that are in those. And that ties back into, you know, what if we just look at a 1% efficiency gain? Now, there's nothing for free here, but looking at particular areas, and if we can just make 1, 2, 3% efficiency gain in the way we do things by using the Internet of Things, it can make a huge difference, and there's a lot of money on the table here. So we saw IoT, it presents a lot of challenges. Connectivity was a challenge, compatibility was a challenge, the huge scale was a challenge, but our hardest challenges was actually getting the data from the actual car up to the server. You know, that gap between the dongle and the HDD post was the hardest thing. But if you can bridge those gaps, you know, Spring XD really makes the rest really easy. We wish we could have shown you more code and more complexity, but on Spring XD, there just wasn't a whole lot. It was really easy to do. It was really easy to connect the pieces. So let's go ahead and open it up for some more questions for anyone here. Yeah, so the question is, can we talk about scaling of the prediction algorithm? And I think one key thing when it comes to either prediction algorithms or rules engines is how you can partition the data. So Spring XD has built-in support for partitioning. So as we start to run multiple instances of the modules in our stream, you can effectively have multiple kind of parallel instances of that stream running. And then because you've partitioned the data, hopefully on something that makes sense, so you might partition it based on, you know, VIN number. That way you're going to know that every message for a particular VIN is going along one path, so it's hitting the same nodes. So you can then ensure that if you're running multiple instances of that, that prediction model or that rules engine or CEP or whatever you want to call the technology, it's getting all the data that needs to kind of be co-located in one place and can start to run. But you're certainly going to have to partition it. If it comes down to a single point, that would be a bottleneck as well. So I think partitioning is the kind of the key thing there. Any other thoughts?
The only other thing I would add is the fact that the data science piece was written in Python. It's running as an external process. So because we can scale that independently, that's really, from a processing standpoint, that would be the closest to a bottleneck we've got. So with Rabbit, we're able to scale that Python process out and get that running in parallel independently of the Spring XD pieces as well.
Yes? Well, we needed to run on a phone that we had, and I think the four of us have iPhones.
Yeah, we're all iPhones, and the developers that were conveniently available are iOS guys. Yeah, there's no technical reasons for it.
Yes, sir. So, question on. Yeah, so questions around security, around IoT or not. Mm-hmm. Mm-hmm.
Well, there's a couple different aspects to that, right? First is there's an industrial piece of this where that concern is much, much, much less. Like everything in the GE video, I don't think Southwest really cares if they're purposely streaming data on their jet engines. But a better example would be like Nest, because Google owns Nest. Now with Nest, they understand essentially when you're home, because they can tell just by the up and down temperature swings. That's probably one of the reasons they bought them, is because they'd be able to identify that. Yeah, that's it. Because you're buying the piece, you're right. With our government, it's kind of you bought into it. You're giving up that. I don't know if anybody else has any chimes in, but it's kind of a buyer beware kind of thing. I mean, let's be 100% realistic though here. If the government told you that you have to wear a tracking device 24/7 at all times, would you do it? No. Yet you carry this around 24/7, 365. It's the exact same thing.
So yeah, I would say with the connected car, yeah, we didn't really go too much in security at all. We definitely could track Phil and Darrel around quite a bit. They say they're lost. Oh, let's go find out where you are and how you need to get there. With some of our other customers, they certainly would not be running in this necessarily in the public cloud, but the servers and where all the data is going would be their own private cloud. So then the security concern would be going into securing that data in their own infrastructure rather than hosting that publicly. That's probably the biggest concern we see right now.
Actually, we did have one conversation with, let's give this to the whole, we'll give this technology to the sales team and to all the engineers just to gather more data. And there was a lot of conversation about, wouldn't that be interesting to see where everybody really is during the workday. But we haven't gotten there yet, but it does bring all that stuff up.
But very good point. Other questions? So we do have some more resources if you're interested in finding out more on Spring Framework, Spring Boot, Spring XD, as well as some other places to find information, videos, further contacts. Legal disclaimer on our icons, and that's it.
Thank you, everybody.
Thank you.